So I assume that by now you must be knowing that what is forward propagation and what are the different steps involved in forward propagation. So in what we do in forward propagation is we try to pass our input to our neural network. And what happens is that this input gets multiplied to respective weights, and a bias term is also added, and all these things happen during the step one. And after that, this value gets passed towards the activation function in the step 2. So in this video, we will be learning that what is activation function, where do we use activation function, what is the concept of linearly separable and linearly unseparable, and why do we need activation functions. And at last, we will be discussing about different types of activation functions. So without wasting any time, let's get started. So what is activation function? So in a neural network, activation function is a kind of stuff that tries to define the output of a neuron with respect to some input. So whenever we pass the input to our neuron, we get the output through that neuron by activation function. So where do we use activation functions? So in all the neural networks that you will be encountering in your later in the future and in later videos, whatever kind of neural network that you design, whatever neural network you try to study, whatever neural network you make, you have to include activation functions. In all the neural networks, during the forward propagation step, activation functions are involved. Before we discuss that why do we need activation functions, let us learn the concept of linearly separable and linearly unseparable. So in linearly separable, what linearly separable says is that whenever we classify our data set, whenever we have two classes and we want to separate them, we want to classify them, and they can be classified with the help of a single line. For example, in this case, in this example, what we are doing is we are trying to separate the circles and the crosses by using a straight line. And since the straight line has been used here, therefore this is an example of linearly separable. But in linearly unseparable, we cannot classify the two classes just by a straight line. For example, here you can see that there are several crosses, and within the crosses there are some circles. And in order to separate these two categories, in order to separate these two classes, we have drawn a different shape. Here we have drawn something like a circle. So because we are not using a line to separate our classes, therefore this is a concept of linearly unseparable. Whenever we draw a line, we use the equation y is equal to mx plus c. But whenever we draw a little complex shape or any other kind of shape, we use some complex functions. So in linearly unseparable, the two classes can't be separated by a straight line. So in linearly unseparable, we use some complex shapes, we use some complex functions in order to generate that complex shape in order to classify our objects or in order to classify our data sets. So why do we need activation function? All of us know that the real world data that we get is not linearly separable. We cannot classify the data in practical life, in real world, just by a straight line. For example, here we don't get data set, or we don't always encounter data set. It might be possible, but in majority of the cases, we don't encounter a data set that can be separated, where the classes can be separated just by a straight line. We have to use a complex function in order to generate a complex shape, in order to separate our data set. So we can say that a real world data set is non-linear. Therefore, it can't be separated by a straight line. Therefore, it is linearly unseparable, which means that we need some more complex functions in order to classify or predict the data that we are working on. Here I have a neuron. I have a diagram of a neuron. So what I'm doing is I am passing some inputs. These inputs are getting multiplied to the respective weights, and at last some bias is added. So during the step 1 here, what I'm getting is I'm getting equation like this: x1 w1 plus x2 w2 plus something something up to p. So here you can see that this resembles the equation of a line. This resembles the equation of a straight line, of linear regression. So we just discussed that linear regression, or I can say that linearly separable or I can say that straight line cannot separate real world data. We need some complex shapes, and in order to get the complex shapes, we need some complex functions. So what we do is we attach a activation function here. So what does the activation function do is it tries to transform this linear equation line into some other equation, a more complex equation. Once we use this equation, what we get is we will get a non-linear output, and therefore we will be able to separate our data more accurately than in this case. That's why we use activation functions in first place, in order to separate our linearly unseparable dataset. The input that we get here, the input that we feed to our neuron, is not always going to be linearly separable. Therefore, we use activation function in order to classify our classes, in order to make predictions much more accurately. So let us discuss that what are the different kinds of activation functions. So we have sigmoid, we have tanh, and whatever the problems that sigmoid and tanh were posing, they were resolved by using ReLU. So we will be discussing about sigmoid, tanh, ReLU, leaky ReLU, PReLU, ELU, softmax, swish, maxout, softplus, mish, and at last GLU. So these are all the different types of activation function that we will be encountering in the upcoming videos. Each video will be dedicated for each separate activation function. So in this video, we discussed that what is activation function, where do we use activation function, what is linearly separable and linearly unseparable, why do we need activation functions, and what are the different types of activation functions. So that was all for today, guys. In the next video, we will be covering about sigmoid activation function. So let's meet in the next video. Until then, bye bye.